Okay, so welcome back to this next video in which we are discussing group automorphisms. Okay, so we've now proven that the set of all automorphisms of a group capital G actually forms a subgroup of the symmetric group on the group capital G. Okay, so it is in fact a group in its own right. So I should now say the group of automorphisms of the group capital G. Okay, right. So in this next video, what we want to talk about now is the concept of an inner automorphism. Okay, but firstly let me just motivate where we're going to go. Okay, so I have now shown you what an automorphism actually is. We've seen that it's one of these set permutations of the set that underlies the group that is actually an isomorphism of the group onto itself. And we said that the identity set permutation, the identity map which sends all of the elements of the group onto themselves, that is always a group automorphism for any group capital G. Okay, but that's not a very interesting group automorphism. We saw an example of a really interesting one in C3 which was not equal to the identity map. Okay, what I want to do now, however, is discuss for a more general group how you can actually find some interesting group automorphisms, and a bunch of interesting group automorphisms that you can usually find unless your group is abelian. Then we'll discuss why it doesn't work if your group is abelian. Okay, but in a non-abelian group, some easy interesting automorphisms that you can find are the inner automorphisms. So we're now going to discuss a way of actually finding some automorphisms for a group. Okay, right. So firstly, we need to discuss conjugation, okay, because conjugation is going to be extremely important. Inner automorphisms is absolutely everything to do with conjugation. So I'm just going to remind you about the fact that we can always construct a group action by a group capital G on itself, where the elements of the group act on other elements of the group by conjugation. Okay, now we discussed this in the video on the class equation previously in this playlist on group theory, but I want to repeat the information about this here, okay, because it is so important for what we're about to discuss. Okay, so conjugation then, we can use conjugation to have a group action by the group capital G on itself. Okay, so we've got our group capital G here, and we're now going to have a group action. Now remember, a group action, the nice easy way to interpret what a group action is that it's a composition table where you put all of the elements of the group down here. Okay, so you give absolutely all of the elements of your group, and I'll just colour my group in red here. You give all of the elements of your group a row in the group action composition table, and then up here, the columns, you dedicate the columns to the set on which the group is going to act usually. However, in this case, the set on which the group is going to act is actually the group itself, the set that underlies the group. Okay, so we're actually going to put all of the elements of the group up here as well, so all of the columns are going to be dedicated to elements of the group, just like the rows. Okay, so we'll put all of the elements of the group up here as well, and as usual we'll call the group action composition dot. Okay, so how are we going to define this? Well, we're going to define it using conjugation in our group composition law. Okay, so if I want to define what little g dot little a is, where little g is taken from this portion, so it will be a row corresponding to the element little g. So here is the row corresponding to little g, so it's taken from the red portion basically. Okay, and little a will be taken from our turquoise portion here. Okay, so it will have a column dedicated to it, and I might just try and squeeze it in there. Okay, so here is little a. So if I want to define what g dot little a is, which is this entry here in my group action composition table, the way I'm going to define it is I'm going to say, okay, g and a are both elements of the group, so what I'm going to do is I'm going to conjugate little a by little g. So I'm going to take GA, G inverse in this way, the G conjugate of little a, where all of these compositions here are compositions in the group composition table. Okay, so that's perfectly valid. We will get some other element of the group, so this is looking good, because all of the entries now in this group action composition table are going to be back within the group, and of course the group is the set on which the group itself is acting, so that's good. Okay, all of the entries in our group action composition table are going to be from the group, from the set here. Okay, so from the turquoise set, which is the group. Okay, so that's looking hopeful that this is going to be a group action, but of course to be a group action it needs to obey the two axioms of group actions. Okay, and it's those that I want to check now. Okay, so this is quite nice and simple to check. So let's now check axiom number 1 firstly. Okay, so axiom number 1 of a group action says that for all little g1 and little g2 that you pick from the group, okay, so for all little g1 and little g2 you pick from the group, and these we're picking from the from the red portion over here, and for all little a that you pick from the group, okay, and this time we're thinking about the turquoise portion over there, it must be the case that g1 dot g2 dot a, okay, so firstly act g2 on a, then act g1 on the answer to g2 dot a, that must be equal to g1 composed with g2, where this is composition in the group composition table, and the answer to g1 composed with g2 acting on the element little a. Okay, so basically this says that the group action composition table must be consistent with the group composition table. Okay, so we better make sure that for this definition of our group action that we actually do have this axiom satisfied. Okay, so let's take the left hand side here and turn it into the right hand side. So for any g1 and g2 and little a that you can possibly come up with, let's consider what is, oops, I missed off the little dot there, g1 dot g2 dot a. Okay, so just now apply the very definition. So we'll start by applying the definition to g2 dot a here. Okay, so g2 dot a is going to be the g2 conjugate of little a, so I can just replace g2 dot a here with g2 a g2 inverse. Okay, so little a conjugated by little g2. Okay, so that is going to be the answer in here. Then what I'm going to do is I'm going to act little g1 on this answer. Okay, so I'm going to take g1 dot this answer, and of course that involves conjugating this answer by little g1. So I'll have g1 that side and g1 inverse on this side. Okay, and then that will now be the entire left hand side here. Okay, so all I've done there is applied the very definition of what the group action is defined to be doing. Okay, now what I'm going to do is I'm going to rewrite this in a clever way. Of course, all these four compositions that we've got here, okay, we've got a composition symbol here, a composition symbol here, composition here, and composition here, they're all in our group composition law. Okay, and we know that our group composition law obeys associativity, so this term, this expression here, has one and only one answer. It really does not matter where I put the brackets. So I'm just going to change where I put the brackets. So I'm going to put brackets around g1 composed with g2 at the start there. So I'm going to associate those two together. Then we'll have the a in the middle, and now I'm going to re-express this g2 inverse composed with g1 inverse. And of course you'll probably realise that that is equal to g1 composed with g2 inverse. So when you have g2 inverse composed with g1 inverse like that, that's the same thing as g1 composed with g2's inverse. Okay, so if you take g1 composed with g2 and compose it with this thing, g2 inverse composed with g1 inverse, either way round they give the identity element. Okay, so these two things are utterly equivalent. So g2 inverse composed with g1 inverse is exactly the same as g1 composed with g2 inverse, basically. Okay, and what we can see here, so I've again just rewritten it, nothing dangerous here, this is all allowed, all I've done is rewritten it basically. Okay, and now it's very obvious that this is just the very definition of g1, g2 acting on little a, because this is little a conjugated by G1 composed with G2, and that's the very definition of what it means for G1 composed with G2 to act on little a. So indeed, I've started with the left-hand side here, and I've turned it into the right-hand side of my equation, and these arguments that I've just applied, they are totally valid no matter what little G1, no matter what little G2, and no matter what little a you dream up from the group, basically. Pick whichever ones you like. This argument is totally valid. Okay, so we've shown now then axiom number 1 of group actions, okay, is satisfied by this action of the group on itself by conjugation. Okay, let's now turn our attention to axiom number 2 of a group action. So axiom number 2 of the group action relates to the identity element of the group. So it says that the identity element dot A must equal A for all little a that you can possibly pick from the turquoise set, but in that case it's our group. Okay, so for all elements of the group, little a, it must be the case that when you act the identity on them, it just gives them the same element back again. Okay, so why is that true? Well, let's again just apply the very definition of what it means for the identity element to act on an element little a. Okay, well that means conjugate little a by the identity element. So take the identity, a, and then the identity's inverse. But what is the inverse of the identity element? The identity element's inverse is just the identity element. So here we're just going to get the identity composed with a composed with identity, and of course that is equal to little a, no matter what little a you have there. Okay, because the identity element composed with anything either way round just gives anything back again. Okay, so indeed the identity element does act on any element of the group to give back that element of the group. Okay, so this is a group action. Now, what does that actually mean? Well, what is the whole idea behind group actions? The whole idea behind group actions is that it allows you to associate with all of the elements of the group, in red here, set permutations of our set in turquoise up here, which in this case is our group. Okay, so what we can use this group action of the group on itself by conjugation to do is associate with all of the elements of the group a set permutation of the group itself. And what is more, these set permutations that you can associate with the elements of the group, they will, their composition as set permutations will be consistent with the composition law of the group. Okay? So, let me show you how we do this then. So, if I've got some little g, which is an element of my group, capital G, okay, and of course I'm picking it really from the red portion here, okay, I can associate little g with a set permutation of my group, and I'll call this set permutation sigma little g, okay, and it's going to map all elements of the set, which in this case is our group, all little a in our group quite simply onto g dot little a, okay, but of course g dot little a is just little a conjugated by little g. Okay, so this then is the set permutation that I can associate to any element of the group. Okay, and what this being a group action tells us is that these set permutations, which I can go through and associate to all the elements of the group, their composition is going to be consistent with the group composition law. And what that means is that if I have two elements of the group, G1 composed with G2, sorry, don't compose them yet, let's just say I've got two elements of the group, G1 and G2, okay, then what I can do is I can come up with their set permutations that are associated to them, okay, and if I compose these two set permutations together, so if I say firstly do sigma g2 and then do sigma g1, so I compose them together, the answer to that will be the same as if I compose the two elements together in the group. So if I do g1 composed with g2 in the group, and then take the set permutation that's associated with that. Okay, so the group composition law describes the composition of the set permutations that you're associating with all of the elements of the group through this group action. Okay, right. So, conjugation then, it describes these set permutations of the group, basically. Okay, now we are discussing group automorphisms, so what do you think my next line is actually going to be then now? Okay, well here it comes. In fact, Actually, wait 1 second. I'm going to say one more thing before I actually go on to the fact that these set permutations are all automorphisms. Okay, I'm just going to make the comment about what if G is abelian. Okay, so conjugation, these set permutations that you can associate with all the elements of the group, which are set permutations of the group itself, these are usually interesting set permutations. However, they will be really boring if the group is abelian. So if our group, capital G, is abelian, then conjugation has absolutely no effect. Okay, so if G is abelian, then if you take whatever A you like and whatever G you like, and you conjugate little a by little g, it has absolutely no effect. And the reason is that if the group is abelian, you can just interchange any two things in the group. In this expression here. Okay, so the composition will be commutative, so you can just swap around G composed with A for A composed with G, and then the G will cancel with the G inverse, so you'll just get that this is equal to little a. So if it's abelian, then conjugation of A by G just always gives A, no matter what little a is and no matter what little g is. And that means that you end up with all of these elements of the group being associated with the identity set permutation of the group. Okay, so they'll quite simply map all elements of the group little a onto themselves, so that all little g will be associated with the identity set permutation. Okay, so the group action of a group on itself by conjugation is only interesting if you're working in a non-abelian group. It's not interesting at all if you're working in an abelian group. Okay, so my next line then, finally, these set permutations that you can associate with all of the elements of the group and the set permutations of the group itself, where you send all elements of the group to what the element is conjugated by little g, okay, these are all automorphisms, always automorphisms. Even if you're working in an abelian group, they're always automorphisms. I mean, it's a bit trivial because all of the elements of the group are just associated with the identity set permutation, but it's still an automorphism. Okay, so conjugation is always an automorphism, and these special automorphisms, which are set permutations associated with conjugation by some element of the group, okay, these are what are called the inner automorphisms. Okay, so what I want to show you then is why these set permutations associated with the elements of the group through conjugation by that element of the group are actually automorphisms. Okay, so first I'll just write inner automorphisms down. Okay, so these special automorphisms which relate to conjugation of all of the elements of the group by some fixed element of the group, these are called inner automorphisms. Again, that's what we now want to study. Okay, right, so I want to now explain to you why it is that one of these set permutations associated with conjugation by a certain element of the group is actually an automorphism. Well, we are half there. We know that they are set permutations of the group onto itself, okay, because that's true whenever you have a group action. The group action associates with elements of the group set permutations of the set on which the group action is acting. Okay, so because we have a group action of the group on itself involving conjugation, we have set permutations. Okay, so whatever little g you take, sigma little g will always be a set permutation. What I now need to prove is that sigma little g obeys the isomorphism criterion. So what I need to prove now is that for all, let's say, little a1 and little a2 that you can possibly pick from the group, sigma little g, this set permutation of the group that involves conjugation by little g, of a1 composed with a2, where this is composition in the group, is equal to sigma g of a1 composed with sigma g of a2. Okay, this is just the isomorphism criterion. Yes, we've changed the symbols in it a little bit, but it is still the isomorphism criterion. Okay, so we want to check this, and then we'll know that sigma g is indeed a group automorphism of the group capital G. Okay, so how are we going to prove this? Well, we're just going to go straight to the definition of sigma g. Okay, so sigma g, where's it going to send A1 composed of A2? Well, it's just going to send it right onto the little g conjugate of A1, A2. So put A1 composed of A2 in the middle and conjugate it by the element little g. So the left-hand side of this equation just becomes g A1, A2, g inverse. Okay, then let's have a look at the right-hand side of this equation. Okay, so again, we'll just apply the definition here. So sigma g A1 is just going to be the g conjugate of A1. So we'll get g A1, g inverse, and it's going to be composed, where this is composition in the group, with sigma g A2, which again will be g A2, g inverse, so the g conjugate of A2. Now, why is that fantastic? Because the g inverse and the g here, those are going to cancel to give us the identity element, and therefore we might as well not have that at all. So this becomes, whoops, not g1, g A1, A2, g inverse, okay? So it becomes the exact same thing that we have on the left-hand side here. Okay, so indeed, the left-hand side is always equal to the right-hand side here, no matter what little a1 and no matter what little a2 you pick from the group. Okay, so what I've just shown you is that no matter what little g you take, sigma little g, this set permutation associated with the element little g, and it's a set permutation of the group onto itself, defined by conjugating all the elements of the group by little g. It is actually a group automorphism, and it's called an inner automorphism of the group capital G. Okay, right, so for my next trick then, what I want to show you is that this collection of inner automorphisms, okay, and I should probably just give you a bit of nomenclature here. So what we can do is we can collect up all of the inner automorphisms of G. Okay, so we can go through all the elements of the group and we can use them to construct a sigma little g. Okay, so we can use them to conjugate all of the elements of the group and have a look at the set permutation that that creates. And we can collect all of these distinct set permutations together into a set, and the set is then called the inner automorphisms of G. Now let me just make an important point. For all the groups that you look at, it is not necessarily true that if we have two distinct elements of the group, G1 and G2, that the set permutation associated with G1 by conjugation is necessarily distinct from the set permutation associated with G2 by conjugation. Okay, so the most vivid example is obviously in the case of an abelian group, okay, where all of the elements of the group, if you use them to construct these set permutations, they all are telling you about the identity set permutation. They all correspond to the identity set permutation. Okay, so what I'm trying to say here is that if you go through all of the elements of the group and use them to construct these automorphisms, okay, it's not necessarily true that if you have two distinct elements in the group, that conjugation by them will actually create you a different set permutation. A different group automorphism. It might do, but it's not necessarily going to be true for all the elements of the group. So what you'll go and do when you're collecting up these inner automorphisms to put into this set is you'll just put in distinct ones, basically. You won't obviously put two identical set permutations in twice, okay? You'll put in the different ones, okay, and you'll put each one represented once, basically. Okay, so you collect together all of the inner automorphisms that you can find by using every single element of the group to conjugate all of the elements of the group to create one of these group automorphisms, and you stick those into a set, and this is denoted in G, the inner automorphisms of G. Now clearly this is a subset of the set of all automorphisms of G, which we know itself is a subgroup of the symmetric group on the group capital G. Okay, what I want to do, my next trick, is going to be to show that this subset of the automorphisms of G, the inner automorphisms of G, that this is in fact a subgroup. Okay, so I want to replace this is a subset of with is a subgroup of. So I want to show that the set of all inner automorphisms of the group capital G is actually a subgroup of the set of automorphisms of G. Okay, right. So once again, to show that a subset is a subgroup, you need to show that with the inherited composition law that it has from the set, or rather from the group of automorphisms of the group capital G, the larger group, that it actually is a group in its own right. So it obeys the axioms of group theory, and again I will remind you that we don't need to worry about axiom number 2, we get that automatically because this is a group, and in fact we could view the inner automorphisms of G as a subgroup of the symmetric group on the group capital G, because after all it is a subset also of that. Okay, right, so we just then need to check axiom number 1, axiom number 3 and axiom number 4 of group theory are satisfied by this set of all inner automorphisms of the group capital G. Okay, so let's start off with axiom number 1. Okay, so axiom number 1 is closure. So we want to prove that if we compose together two inner automorphisms of G, two automorphisms that correspond to conjugation by elements of the group, that we end up with another automorphism. And we know that we end up with another automorphism because, after all, these inner automorphisms are automorphisms. Okay, so when you compose two automorphisms together, we know you end up with another automorphism. Okay, so when we compose two inner automorphisms together, we know we'll end up with another automorphism, but we want to show we end up with another inner automorphism. Okay, i.e. another automorphism that can be interpreted as meaning conjugation of all of the elements of the group by some other element of the group. Okay, right, so I want to show that if I have sigma G1 and sigma G2, so two inner automorphisms, so these are two automorphisms that are in the set of all inner automorphisms, what I want to show, okay, and I should put a for all there, okay, and I'll just underline this in a nice colour. So for all inner automorphisms that I can pick, I want to show that if I compose these two together, okay, so if I take sigma G1 composed with sigma G2, where remember this means composition in the symmetric group on the group capital G. So this means composition of the set permutations. It means do the set permutation sigma G2 first, then do the set permutation sigma G1 second. I want to show that the answer, which I know is another automorphism, I want to show that it's actually another inner automorphism. Okay, so how am I going to do that? Well, I really don't need to worry about this because of the fact that I had that group action, and I'm just trying to find my previous piece of paper. Here it is. Remember, conjugation was this group action of the group on itself. All of these mappings, all of these inner automorphisms I had, they were the set permutations that this group action associated with all of the elements of the group. And what did I say at the time? That composition of the set permutations was consistent with composition in the group. Okay, so if I want to compose together sigma G1 with sigma G2, I instantly know from the fact that I had this group action that this is sigma of G1 composed with G2. In fact, I've written that down here. Okay, that was what it meant for composition of the set permutations, that a group action associates with the elements of the group to be consistent with composition of the elements of the group in the group composition table. Okay, so I can instantly say that that is going to equal sigma of G1 composed with G2, where G1 and G2 are composed in the group composition table. Okay, but of course this is an inner automorphism because this is a set permutation associated with an element of the group G1 composed with G2. So this is an inner automorphism of G, okay, and therefore I've proven that if you take any two inner automorphisms of G and compose them together, you end up with another inner automorphism of G. So this subset of inner automorphisms of G is in fact closed under composition. Excellent. Okay, next up we need to make sure that axiom number 3 of group theory is satisfied. Okay, now axiom number 3 of group theory says that we must have an identity element. Okay, and for subgroups this means that we must contain the identity element from our larger group. Okay, so we must contain the identity set permutation. Okay, so why is the identity set permutation an inner automorphism? Why is it one of these automorphisms that can be thought of as representing conjugation of all of the elements of the group by a fixed element of the group? Well, it's because if we consider what sigma of the identity is, this is the map that corresponds to conjugation by the identity element. What do we know about conjugation by the identity element? We know that it has absolutely no effect, even in a non-abelian group. When you conjugate any element of the group by the identity element, you get the element of the group back again. We did it here. We conjugated A by the identity element and we got A back again. So it is always associated with the identity set permutation of the group. Okay, so that will therefore be a group automorphism, and it is therefore indeed an inner automorphism because it satisfies the definition that we can think of it as conjugation by some element of the group. Okay, so the identity set permutation, the identity automorphism, is in fact an inner automorphism. So it is within our set of all inner automorphisms of the group G. Okay, and the fourth and final axiom, okay, we want to prove that for any inner automorphism that we have, so for all inner automorphism, and I'll just call this sigma G, which is an element of the inner automorphisms of G, we want to prove that the inverse for sigma G, the inverse map, is also an inner automorphism. Okay, and the way that we can do this is quite simply, we know what the inverse for this is going to be. It's going to be the set permutation associated with the inverse element for G in the group. Okay, so this is in fact going to be the inverse set permutation for sigma G. Okay, all I now need to do is prove that, and I know that this is an inner automorphism. So the instant thing that I know is that sigma G inverse will be an inner automorphism. It just means the set permutation associated with this element G inverse using the group action of the group on itself by conjugation. Okay, and it certainly therefore is an inner automorphism of G. All I need to prove is that this is the two-sided inverse of sigma G, and then I will have shown that sigma G has a two-sided inverse in this subset of inner automorphisms of G. Okay, so the way I can do this quite simply is again by remembering that composition of the set permutations associated to the elements of the group by the group action is consistent with composition of the elements in the group. Okay, so if I consider what sigma G composed with sigma G inverse is, okay, again that's just going to equal sigma G composed with G inverse, where this is composition of elements in the group. And this, of course, meant composition of the set permutations that they represent. Okay, but of course, G composed with G inverse is equal to the identity element, so this will then be the set permutation associated with the identity element, which is, of course, the identity map. So these two set permutations have composed together to give the identity map. Okay, so that means that sigma G inverse here, okay, the set permutation associated with G's inverse in the group is in fact the inverse map for sigma G. Okay, so this is the inverse set permutation for sigma G. Okay, and of course to completely conclude that I would have to do it the other way around. I want to prove that it's a two-sided inverse, so if we do it the other way around, sigma G inverse composed with sigma G, then of course it'll just be sigma G inverse composed with G here, and again G inverse composed with G is equal to the identity in the group, so again this becomes the set permutation associated with the identity element, which we know is the identity set permutation. Okay, so that now shows then that this set of all inner automorphisms of G, all the automorphisms that can be interpreted as conjugation of the elements of the group by a fixed element of the group little g, okay, this is in fact a group in its own right, and it's a subgroup of the group of all automorphisms of G, which itself is a subgroup of the set, or rather the group of all permutations of the group capital G, which is the symmetric group on the group capital G. Okay, right, and with that we will conclude our discussion of group automorphisms for now.